Hi friends, welcome to my YouTube channel. Today we are going to discuss about the vertical stress due to a concentrated load using Boussinesq'S theory. We are just evaluating the stress due to a concentrated load. So coming to the introduction part, Joseph Valentin Boussinesq, 13 March 1842 to 19 February 1929, was a French mathematician and physicist who made significant contributions to the theory of hydrodynamics, vibration, light and heat. In 1885, Boussinesq developed the mathematical relationships for determining the normal and shearing stresses at any point inside a homogeneous, elastic and isotropic mediums due to a concentrated point loads located at the surface, using logarithmic stress function for the solution of elasticity problems. The Boussinesq developed some relationships about how to determine the normal stress and what shear stresses at some point inside a homogeneous, that is, the material is same throughout the medium. The material is elastic. It will be able to regain its original shape after the load is removed. And isotropic, that is, the mechanical properties remain same in that medium, okay, due to a concentrated point load. Because of this concentrated point load in these materials, whatever the normal stresses and shear stresses are developed, there will be some relationships between that, so that are evaluated by this Boussinesq. Okay, coming to the introduction part, we also have assumptions to discuss about. So the first assumption is the soil mass is an elastic continuum having a constant value of modulus of elasticity, that is the ratio between stress and strain. See, I told you E is equals to stress by strain. I also explained you in the previous video about this. Okay, here the E, the Young's modulus or modulus of elasticity, is constant for this medium, and also it is an elastic continuum. As already explained, elastic continuum means it will be able to regain its original shape. The soil mass is homogeneous, okay, and the soil is isotropic, that is, it has identical properties in all directions. We are just talking about the mechanical properties when the term isotropic is coming. Okay, whenever we are talking about homogeneous, that means the material is same throughout the medium. Okay, the soil mass is semi-infinite, that is, it extends to infinity in all directions except on the top horizontal plane. Except on the top horizontal plane, in all other directions, the soil mass is infinity. Okay, see, I will explain you. Whenever we are talking about some foundation, we will take the soil. See, or I will just show you in this view. Okay. Okay. See, this is the foundation we are talking about. The soil next to this on the right hand side is infinity, right? And also to the left hand side it is infinity, and also to the bottom it is infinity. But whenever we are talking about the surface that is above the foundation, that is not infinity, as it is simply the depth of foundation. Okay, so we are taking it as semi-infinite, where it is finite in all the three directions except the top direction, except the top horizontal plane. Okay, the soil is weightless and is free from residual stresses before the application of load. We are not taking the self weight of the soil, we are taking it as negligible value. Okay, we are thinking that before the application of load, whatever the residual stresses are there, that are negligible and are not considered in this. Okay, these are the basic assumptions of the Boussinesq theory. Okay, next, going to the derivation part. Here we have a figure showing a horizontal surface of the elastic continuum. See here, subjected to a point load Q at a point O. See, this is the rectangular diagram we are taking, where we are taking a point O inside this, that is subjected to a point load. Okay, point load Q. The origin of the coordinates is taken as O. We are taking the point O as the origin. Okay. Next, using logarithmic stress function for the solution of elastic problems, the Boussinesq'S proved that the polar stresses sigma r, okay, sigma r is nothing but the polar stress at point P, okay, which is having coordinates of x, y and z, x, y and z with respect to O, as that is the origin we have considered. Okay, see, this is the point z, that is the depth, it is the x and it is the y axis. Okay, we are just taking the coordinates of that. So whatever the polar stresses developed at the point P, because of this Q, because of this point load at O, okay, which is the origin, is given by this equation. Sigma r is equals to 3 by 2 pi q cos beta by r square, wherein this equation r is nothing but the polar distance between the origin O and point P. See, here in this diagram we can see this is the origin O and this is P. Whatever the vertical distance is there, we are denoting it with Z. But R is nothing but the polar distance. See, this is R, right? Okay, this is R, the polar distance. Whereas beta is the angle with the line OP, which the line OP makes with the vertical. See, this is OP, right? This is the OP line, that is nothing, that is denoted by the distance R. This makes an angle with the vertical, that is beta. Okay, that is beta. So obviously R is nothing but, see, this is the R, right? R is equals to under root of x square plus y square plus z square, x square plus y square plus z square, or R is equals to under root of small r square plus z square. See, in this diagram I will show you, this is the capital R, okay, but here we have a small r. So from this diagram, the r square is equal to small r square plus z square, if we are considering this diagram. Okay, and sine beta is equals to, sine of the angle is nothing but opposite by hypotenuse. Hypotenuse is r, capital R, right? So this is the angle, this is the opposite, and this is the hypotenuse. So again it is small r by r, whereas cos beta is adjacent by hypotenuse, that is z by r. Okay, the vertical stress, so the vertical stress at a point P is given by sigma z is equals to sigma r cos square beta. So this is the formula where we know sigma r is equals to 3 by 2 pi q cos beta by r square. Okay, this is the sigma r value, it is multiplied by cos square beta. So sigma z is given by 3q by 2 pi into cos beta into cos square beta, right? So it is cos cube beta by r square. So that is, we know cos beta is equals to z by r. Substitute that value over here. So 3q by 2 pi cos beta is equals to z by r. So whole cube of that value divided by r square. Okay, so we are just taking this r cube to the denominator. So 3q by 2 pi multiplied by z cube by r to the power of 5. So this is the formula. Sigma z is equals to 3q by 2 pi 1 by z square, z power 5 by r power 5. Okay, so we are just multiplying and dividing it with z square. This is the equation of vertical stress due to a concentrated load using Boussinesq's theory. So now we'll substitute the value of r in this. We know the capital R is equals to under root of small r square plus z square. So we'll substitute the value of this r in this. Okay, then the equation would become in this way. where 3 cube by 2 pi and 1 by z square will be outside the bracket, and inside the bracket we have z power 5 and we have r square plus z square 5 by 2, that is under root of this value, right? So we have r to the power of 5, where r is nothing but r square plus z square to the power of 1 by 2 whole to the power of 5. So it is simply 5 by 2, right? Next, 3 cube by 2 pi 1 by z square 1 by, we are just dividing this z power 5 by this. We are writing this equation. So it is 1 plus r by z whole square, this square only for this term, whole to the power of 5 by 2. Okay, so this is the equation. This is the vertical stress developed due to the point load because of this Boussinesq equation. Whereas we are taking this 3 by 2 pi into 1 plus r by z whole square to the power of 5 by 2 as IB. We are taking it as some constant over here. See, this is the IB multiplied by q by z square. That is, we are just taking this part. Okay, this q by z square outside and the remaining whole term as IB, where IB is known as the Boussinesq influencing coefficient for vertical stress. Okay, this is the vertical stress equation where IB is the constant. Okay, so this is the equation. That is it for this video, guys. In our next video we'll discuss about some important points regarding this Boussinesq equation along with some limitations and applications of this Boussinesq equation. We will see an example regarding this. So please like, share, comment to my channel. Please subscribe to my channel. That would greatly help me. Appreciate you.